Types of aqueous solutions and solubility. We talked about concentration units, specifically molarity. Let's talk about what happens when a solution forms. So thinking about salt water and sugar water, both things that we've experienced. Salt water is a homogeneous mixture. Another word for that is a solution of sodium chloride and water. Sugar water is a homogeneous mixture or a solution of sucrose, table sugar, and water. You stir either of these substances into the water and it seems to disappear. You can try this at home. How do solids, like salt and sugar, dissolve in water? How do they disappear into the water? Well, when we put a solid solute into a liquid solvent, there's competition between different attractive forces. We'll talk about the nature of these forces later. For now, we're just going to say they exist. So there are attractions between the particles in the solute. So between the sugar molecules, between the ions in the salt. Otherwise, that substance would not be a solid. There has to be something that holds the particles together so it will be a solid. There are attractions between the molecules of the liquid solvent. Otherwise, it wouldn't be a liquid. It would be a gas. And then there are also some interactions that can happen between the solvent molecules and the solute molecules. And so a solid dissolving depends on the relative strength of those different interactions. If the interactions between the solute particles are very, very strong, then the interactions between the solvent and solute particles will not be enough to pull them away. So you can think of these as being people and these being other people. And so if these people are they're really tight with each other. They're just this really tight group, and they're just not interested in meeting new people. They're not interested in getting out and seeing what's going on around them. They're just stuck on themselves, literally. They're not going to dissolve. These people might not be so stuck on themselves, but the solvent molecules might be really stuck on themselves and not let any new people come in to their solution, their liquid. If there's good interaction between the solvent and the solute particles, and the interactions between each group within themselves is not too strong, then everything's going to mix and mingle and you'll have this nice party going on. So in water, there's an uneven distribution of electrons within the water molecule. It's a molecular compound. The bond between the oxygen and the hydrogen is a covalent bond, meaning the electrons are shared. But you can share something, and that doesn't mean it's necessarily shared equally. You think about two people sharing a bed, and oftentimes one person ends up with more of the blankets, right? This happens. So yeah, we're sharing a bed, we're sharing the blanket, but the other person ends up with more of the blanket, and you've got this little corner and you're cold all night. That's kind of what happens with oxygen and hydrogen. Oxygen hogs the blankets, hogs the electrons. Because of that, the oxygen end of this molecule is going to be slightly negative. It's not an ion, it's not a full negative one charge, but it's slightly negative. And this is the lowercase Greek delta. It kind of looks like a D with a posture problem. This means a partial charge. So maybe a third, a quarter, a tenth. It's a little bit of a charge, not much, but it still can be significant. And the other end, the hydrogen end, is going to be slightly positive, okay? So there are interactions between the water molecules, but there are interactions between the water molecules and this ionic compound. So the sodium, the positive ion, is attracted to the negative end of the water molecule. There's good communication here. There's attraction. The chloride, the negative ion, is attracted to the positive end of the water molecule. And so sodium chloride dissolves nicely in water because there's good interactions between the water and these ions. So it happens kind of like this. So here's the sodium cation. And it's going to be surrounded by a cluster of water molecules, almost like a fan group, right? So these are all fans of this sodium chloride, the sodium ion. They're like, oh, we like you, and the groupies, right? They come around, and so the sodium ion lost the interactions it had with the chloride ions in the lump of salt, but those interactions have been replaced by similar interactions with the water. So it's okay with that. So it goes off, and it's surrounded by these little water molecules, and it can float around. And the chloride ion is negatively charged, but water can turn its other side toward the chloride and make it feel comfortable, and it can float around as well. Any questions? Yes?
So if sodium by itself usually has like a violent reaction with water,
Mm-hmm.
in this case when it's separated from the chloride, chlorine, and then it's by itself, it doesn't have any kind of violent
No.
reaction with water.
So, yes, sodium metal reacts violently with water. Here we have sodium and it's not reacting violently. That's because this is a sodium ion. When sodium atoms react violently with water, they become sodium ions. So here, this has all its fight taken out of it. It's happy. The thing is, these sodium atoms form positive 1 ions because in doing so, they have the same number of electrons as the previous noble gas, which is an unusually stable situation in terms of energy. So it's like, I wanted this thing so badly, and now I've got it, now I'm just like, chill, whatever. So it doesn't react with water anymore. Does that answer your question? Yeah. So it is important to understand the properties of an atom and the properties of an ion of the same element are very different. People get all uptight about, oh, there's mercury in my kid's vaccine. Okay, it's not elemental mercury. That would be dangerous. It's mercury in a compound. Very different properties, not dangerous. So the salt dissolves in the water. Now in this solution, we have positive ions and negative ions that are free to move. In this solid piece of sodium chloride, the ions were there, but they couldn't move relative to each other. So because we have ions now, that solution can conduct electricity. Electric current is the flow of electrons, the movement of electrons. So we use the term electrolyte, and you've probably heard that. You know that if you're exercising vigorously and sweating profusely, you need to replenish your electrolytes, right? That is referring to the same types of substances that we use the term for in chemistry, soluble ionic compounds. Electrolytes are substances that will dissolve in water to form a solution that conducts electricity. They form ions, and that will conduct electricity. So if we have, in fact, I woke up at like 4:30 actually. I didn't need to get up till 6. I could not go back to sleep. And I started thinking about how much I want one of these apparatus. And I had one, but it was all corroded and didn't work. And then I was thinking about how I could make one, and it really wouldn't be that hard. So yeah, here I am lecturing about this. It's kind of weird. Sorry about that. So if we have a light bulb attached to a power source, and instead of connecting the 2 wires here, we put the 2 wires into a solution of water. Nothing will happen if it's pure water, because pure water doesn't conduct electricity. But if we throw some table salt in there, it dissolves and forms ions. The ions are free to move. They can carry electric current from one end of the wire to the other. The light bulb lights up. It's kind of cool. So that's what an electrolyte will do. It can conduct electricity. Electrolytes include soluble ionic compounds. Non-electrolytes do not conduct electricity. They don't make ions. So most molecular compounds are non-electrolytes. If we do the same experiment and put sugar in the water, the light bulb will not light up. Because sugar is a molecular compound, it does not form ions in solution. So here's what's happening with sugar and water. So here's a sugar molecule, sucrose. It has oxygens and hydrogens, and those, like in water, are sharing their electrons unequally. Oxygen's still hogging the blankets. So there are small areas of localized partial charges, and the water molecules are attracted to that. So the sugar will dissolve in the water, but it doesn't form any ions. So it's still being surrounded by water molecules, but there are no ions, so it does not conduct electricity. So we've learned a little bit about acids. We learned how to name them and write their formulas. We learned that acids are molecular compounds. When you put them into water, they ionize. So the pure substance, the pure acid, doesn't have any ions, but when you put it in water, it forms ions. And one of those ions is going to be a hydrogen ion. So the molecules are literally pulled apart by their attraction for water. We have two categories of acids, strong and weak. A strong acid is one that ionizes completely. HCl is a strong acid. When you put hydrogen chloride in water, it will completely form hydrogen ions and chloride ions, no intact molecules. Because it forms ions, it is an electrolyte. We call it a strong electrolyte. It conducts electricity. With a weak acid, only a few of the acid molecules form ions. Most of them remain as molecules. So hydrogen fluoride, hydrofluoric acid, acetic acid are examples of weak acids. Here, instead of a single arrow pointing from left to right, we have a double-headed arrow, so it's pointing in both directions. That means that this reaction goes both ways. So it can go forward and it can go in reverse. So what we have with like acetic acid, we've got a picture here. Acetic acid, if you were able to look at the particles in the solution, you would see that most of them are the intact acetic acid molecules. Only a few of them are hydrogen ions and acetate ions. So it does form ions, but only a few ions. It's a weak acid. It ionizes weakly. So strong electrolytes are substances that dissolve completely as ions. There's no intact molecules or anything left. It's just all ions. This includes soluble ionic compounds and strong acids. Strong acids ionize completely. So strong acids are strong electrolytes. These are solutions that conduct electricity well. Weak electrolytes dissolve mostly as molecules, partially as ions. This is mostly just the weak acids. And these solutions conduct electricity only weakly. Now, there should be a slide in here, and someone yesterday asked me, well, how do we know which one is a strong acid and which one's a weak acid? That's an excellent question. So there are 6 strong acids, and you do need to know them. So there's HCl, HBr, HI. Those are the in the halogen family. HF is the little sister, so she's the exception. That's not a strong acid. Then we've got nitric acid and perchloric acid and sulfuric acid. And I can't really give you a great way of remembering those. These are in the halogen family except fluorine, and then you just kind of have to memorize these. Why are these strong acids? Because they ionize completely. How do we know that? We tested it and we found it out. It's not that we put them in a special category, it's just what they do. So how do you know what a weak acid is? They're not strong. There's like a gazillion and a half weak acids. All the other acids are considered weak. So you memorize the 6, and then you know that everything else is a weak acid. Everybody got that list down? It'll be on YouTube later. So here's that conductivity apparatus that I want. Again, this is what happens with a non-electrolyte like sucrose. There's no ions, no electricity passes through. So you've probably heard that you need to be careful using electricity around water. Like you don't want to be using electrical power tools in the backyard while you're standing in a puddle, right? That would be a bad idea. Why is that a bad idea if pure water doesn't conduct electricity? Is the water you're standing in pure water? No. It's probably got some dirt in it, some dissolved minerals. It's not pure water. There's plenty of ions in there to conduct electricity. And you get to the point of lightning, and it really doesn't matter what kind of water it is because, yeah, lightning's just like crazy high voltage. So always be careful of lightning. This is a weak electrolyte, acetic acid. Acetic acid is a weak acid. It's not one of the 6. It forms a few ions, and so what we see with the light bulb is the light bulb glows weakly. This is a weak glow in the light bulb. Weak acid, weak electrolyte. No glow, non-electrolyte. This is a strong electrolyte. Sodium chloride, or one of the strong acids, would do this. We get the light bulb is now glowing strongly. There's lots of ions. It conducts well. Okay? So we've talked about acids dissolving in water, forming ions. That's called ionization. Dissociation is what happens when ionic compounds dissolve in water. Ionic compounds have ions when they're in their pure solid form. They're not forming ions. When we dissolve them, the ions separate from each other, and so the correct term there is dissociation. It's not that we're forming ions. That's what ionization means. We're dissociating. They're just separating. So sodium sulfide, when we dissolve it in water, will separate into sodium ions and sulfide ions. And here's where an understanding of nomenclature comes in handy, because we learned when learning how to write the name of this that we have to look at the 2 individual ions. In Chem 1A, that it's always going to separate into 2 ions, 1 cation, 1 anion. It's not going to be anything else. So if you have something like sodium sulfate, here we have 3 elements. That does not mean we get 3 ions. Sodium is the cation, and sulfate is a polyatomic anion. Polyatomic ions stay together when an ionic compound dissolves and dissociates. Any questions? So ionic compound dissolves in water. Now we have separated ions, and that solution will be an electrolyte. The thing is, not all ionic compounds dissolve in water. So if it dissolves, we say it's soluble. We say it's insoluble if it does not dissolve. And those are qualitative terms. And there is kind of a gray area in the middle, and we kind of solve that by saying slightly soluble. And it is important to understand, this will be covered in Chem 1B, even a compound that's considered insoluble does dissolve to some extent. But it does so to such a small extent that it doesn't matter. You know, if you have 5 ions, pairs, dissociating in a beaker, is that significant? No, it isn't. So that's what insoluble means. It's not a significant amount that dissolves, not noticeable. So solid silver nitrate will dissolve in water. The ions separate, they dissociate, forms a strong electrolyte solution. Silver chloride, you put that in water. Here's a picture of it. It sits on the bottom. You can stir it up. It'll just settle down to the bottom. It's like sand. It just will not dissolve. Doesn't form ions, dissociated ions, right? So why does one dissolve and the other not? Well, there are several factors involved. It's not easy to predict. The best answer is it's complicated. So the best way we've come up with is, so people have done experiments to see which compounds dissolve and which don't. They looked for patterns. We came up with a set of rules. This is an empirical method. You do it by experiment, and it's like, okay, well, this dissolves, this doesn't dissolve. And so that leads us to this table. So you need to memorize the table. It looks like a lot of stuff on there, right? I'm going to show you that it's mostly the stuff on the left that you need to memorize, and a lot of this is redundant. So I'll be crossing some of those things off. So the top half of the table, these are compounds that are generally soluble. So if it has lithium, sodium, potassium, or ammonium ion in it, it's going to be soluble. Over here are exceptions. There are no exceptions. So the best way to use this table is to start at the top and work your way down. So if you're looking at like sodium phosphate, you see it has sodium in it. Sodium compounds are soluble, no exceptions. You don't need to look at the rest. It's soluble. Done. If it doesn't have one of those, see if it has nitrate ion or acetate ion. If it's got one of those, it's going to be soluble, no exceptions. Next is the halides, chloride, bromide, and iodide. Those are soluble with 3 exceptions. So what I'm going to do here is I'm going to get rid of all these words. So let's do this. Come on. We just need to know what those ions are. So if the cation with one of these is silver ion, Hg2+, I didn't mean to cross off part of that. This is mercury 1, or lead 2, then it will be insoluble. But everything else that has chloride, bromide, or iodide will be soluble. So sulfate compounds are generally soluble, except, so let's get rid of these confusing words. So here we've got lead again, and silver again, and then the addition of strontium, barium, and calcium. These are alkali metals. They're the larger alkali metals. So if you get through all of those and you haven't encountered the ions that you have in your compound yet, you go to the bottom of the table. These are generally insoluble. So a hydroxide compound, a sulfide compound is going to be insoluble with these exceptions. So the first exception is if it's got lithium, sodium, potassium, or ammonium in it. Well, if you start at the top and go down and you've got one of those ions, you would have stopped up here, so you don't even need to worry about this. So I'm just going to cross that off entirely. Start at the top and we don't need to think about this. When sulfide pairs with one of these guys, well, let's get rid of the words. Calcium, strontium, or barium, then it's soluble. Those are the same 3 guys that were an exception up here. Okay? So there they were an exception that made it soluble. Here they are an exception that makes it insoluble. And then hydroxide pairing with those same 3 guys, the resulting compound is slightly soluble. Well, usually the difference between slightly soluble and soluble just doesn't make that much of a difference. So we can do it like this. Those are the same, so just forget those. So if you've got hydroxide or sulfide with one of these, it's going to be soluble or slightly soluble. The table looking a little more manageable now. You get down to carbonate and phosphate. Those are generally insoluble, except with these guys. Again, that's the first thing on the table. If you see one of those, don't come down here. You don't need to. So we can cross that one off as well. So that's not so bad. You need to memorize the table. And one of the ways you can memorize it is just by using it. And so there will be lots of things where you have to predict the solubility of an ionic compound. Don't go immediately to the table. Try to think through it first. These are the alkali metals and ammonium. So if it's got one of those, it's soluble. And then work your way down. So try to do it from memory, and then check yourself using the table. And that'll help you to remember this. We do have a green card over here, cardstock page that has solubility rules. They are not exactly the same as the ones in here. I think it's got a little bit more information on there. This is what you need to know for any of my exams. I won't ask you anything that's not covered by this table. Now, it could happen in homework or worksheets or something that it might be something not covered by the table, but it's not on an exam, so you can use other sources of information. Any questions? we should be able to do things like this, predict whether each compound is soluble or insoluble. So here we have nickel sulfide. So we mentally go down the list. Okay, so we probably don't have that firmly in our mental picture gallery yet. Well, we're looking for nickel and sulfide. Nothing there, nothing here, nothing here, nothing there. Here's the first one we come to where we've got one of the ions in our compound. Sulfide compounds are generally insoluble except with those guys. Well, nickel's not one of the exceptions. So, oops, that's not what I meant to do. So then nickel sulfide is going to be insoluble. Insoluble. Okay? Magnesium phosphate. We go down the list. We don't find magnesium or phosphate anywhere in the top half. Let's go back there. No magnesium, no phosphate anywhere here. Not here either. Here we've got phosphate in the bottom. Phosphate compounds are generally insoluble. The only exceptions would have been covered up here, so magnesium phosphate is insoluble. So this one's also insoluble. Lithium carbonate. You go down the list looking for lithium and carbonate. What do you see in the first row? Lithium. All lithium compounds are soluble. No exceptions. We don't need to look any farther. This one's soluble. How about ammonium chloride? Ammonium is also in that first list. Lithium, sodium, potassium, ammonium. This one's also soluble. So any questions? It's a matter of practice, and maybe you need to make some flashcards.